In a laboratory in Nanjing, engineers pointed two beams of light at a receiver sitting across the room and pushed more than 1 trillion bits of data through the air in a single second. No fiber optic cable, no copper wire, just a signal riding on frequencies so high they sit in a band most wireless engineers had spent decades avoiding entirely. That number, over 1 terabit per second, is not a typo, and it is not a theoretical ceiling, calculated on a whiteboard somewhere. It was measured, in real time, using hardware built entirely in-house by a Chinese state-backed research institute. To put that in perspective, the fastest 5G networks operating anywhere in the world today peak at roughly 10 gigabits per second under ideal lab conditions, and deliver a fraction of that in your pocket on an ordinary day. What was demonstrated in Nanjing runs at something in the neighborhood of 100 times that peak figure. This is the technology China is calling 6G, and the race to build it is no longer a distant theoretical competition confined to research papers. It has spectrum allocations, government funding, live outdoor test networks, and a timeline that stretches from a single lab record to an actual functioning city district. If you find stories like this fascinating, hit the like button. It takes real research to put one of these together, and subscribe so you do not miss the next one. Here is what you're about to learn. Why 5G was never going to be the final chapter of wireless technology. The strange physics of the frequency band China is betting on to get to 6G. The actual timeline of breakthroughs that got us here, from a single lab record to a live outdoor network, where the rest of the world stands in this same race. And the very real technical walls, standing between a laboratory record and a phone in your hand that actually uses this technology. Let's start with the problem 6G is actually trying to solve. Why 5G was never the finish line. Every generation of wireless technology has followed the same basic rhythm since the first mobile networks appeared. Roughly once a decade, engineers push into a new range of the radio spectrum, unlock a leap in speed and capacity, and spend the following 10 years building out the infrastructure and devices that actually put that leap to use. 2G made text messaging possible. 3G made basic mobile internet usable. 4G made streaming video on a phone a normal, unremarkable thing. 5G was supposed to do something similar for a wave of technologies that need extremely low delay and extremely high density of connected devices at once. Self-driving cars talking to traffic infrastructure in real time. Remote surgery performed over a wireless link. Factory floors where every machine and sensor talks to every other machine constantly. The honest reality is that 5G has delivered only part of that promise. In most countries, what people actually experience as 5G is a meaningfully faster version of 4G, not the transformative, ultra-low latency network originally promised at its launch around 2019. The full vision of 5G, the version built around extremely high millimeter wave frequencies capable of the speeds originally advertised, turned out to be far harder and more expensive to deploy at scale than anyone expected, because those frequencies do not travel far and struggle to pass through walls, rain, or even leaves on a tree. Carriers around the world scaled back their most ambitious millimeter wave rollout plans once the real infrastructure costs became clear. And by the time most people upgraded their phone to a 5G model, the marketing had quietly shifted toward more modest, achievable claims. That gap between what 5G promised and what 5G actually delivered is exactly the opening 6G research is aimed at. The next generation of wireless technology is not just being designed to be faster. It is being designed around a much bigger structural idea, a single network that blends communication, sensing, and computing. Together, one where the network itself can detect objects and movement the way radar does, coordinate swarms of drones, and feed data directly into artificial intelligence systems in real time, all using the same infrastructure. That also carries your phone call. Reaching that vision requires frequencies far higher than anything 5G ever touched, and that is exactly where the physics gets strange. The terahertz gap nobody wanted to cross. Radio engineers have spent most of the last century working comfortably within a range of frequencies stretching from a few hundred megahertz up to a few tens of gigahertz. Above that range sits a stretch of the spectrum called the terahertz band, sitting between microwaves and infrared light, roughly 100 gigahertz up to 10 terahertz. For decades, engineers half-jokingly called this the terahertz gap, a region of the spectrum that was simultaneously too high in frequency for traditional electronic circuits to generate efficiently and too low in frequency for the optical techniques used in fiber optics and lasers to handle cleanly. It sat in an awkward no man's land between two entire fields of engineering, useful in theory, nearly unusable in practice, the wireless equivalent of a stretch of highway everyone agreed would be useful, but nobody had the right kind of vehicle to actually drive on. The appeal of that band is straightforward once you understand how wireless bandwidth works. The higher the frequency you can transmit on, the more raw bandwidth you have available, and the more data you can physically push through the air per second. In the same way a wider pipe lets more water flow through it in the same amount of time. Terahertz frequencies offer access to enormous, largely untouched chunks of spectrum, hundreds of times wider than anything used for 5G today, spectrum that has sat essentially empty simply because nobody could reliably use it. The problem was never really about how much data terahertz waves could theoretically carry. It was about actually generating, modulating, and receiving a clean, usable terahertz signal outside of a physics lab. The approach Chinese researchers landed on to solve that problem is called photonic terahertz technology. Instead of trying to generate a terahertz radio wave directly using conventional electronics, which is extremely difficult at these frequencies, engineers use two laser beams tuned to slightly different optical frequencies and let them interfere with each other. The difference between those two frequencies lands squarely in the terahertz range, and that beat pattern becomes the carrier signal for the data. Think of it the way two musical notes played. Close together in pitch produce an audible beat frequency. You can hear pulsing between them, except here, the beat pattern between two light waves becomes a usable wireless carrier signal, capable of being modulated with data the same way a radio wave normally is. It is a way of borrowing the precision of optical engineering to solve a problem that pure electronics could not handle cleanly on its own. The timeline of breakthroughs. This idea did not appear overnight, and tracing its actual timeline matters because it shows this is not a single headline-grabbing stunt, but a sustained multi-year research program, one where each step depended entirely on the one before it. In January 2022, Purple Mountain Laboratories, a government-backed research institute based in Nanjing, announced it had achieved a real-time terahertz wireless transmission of 206.25 gigabits per second, using a 360 to 430 gigahertz photonic terahertz system built with Southeast University, Fudan University, and telecom carrier China Mobile. At the time, that result was roughly 10 to 20 times faster than typical 5G speeds, and it was described as the fastest real-time terahertz wireless transmission publicly reported anywhere in the world. It made headlines for a news cycle, and then largely disappeared from public attention, treated as an interesting but distant curiosity, rather than the start of something. The lab did not stop there. By the end of 2023, the same research group had pushed that number past 1 terabit per second in a real-time transmission test, again breaking their own world record and putting the E technology's raw transmission capacity at roughly 100 times what 5G networks are capable of at their peak. That is the specific figure behind the headline claim driving so much recent attention, a genuine, measured laboratory result, not a marketing projection. And it is the number that quietly reset what engineers considered achievable in this part of the spectrum. From there, the program moved out of the lab entirely, which is the harder and more expensive step almost every promising communications technology fails to survive. In April 2026, Purple Mountain Laboratories switched on what it describes as China's first pre-6G outdoor test network based in Nanjing, layering experimental 6G technologies on top of the existing 5G infrastructure already running in the city rather than building something isolated and disconnected from real-world conditions. The launch came alongside a new government-backed investment fund worth roughly $485 million, aimed specifically at Nanjing's development as what officials are calling a 6G city, with support from Huawei, China Mobile, Qualcomm, and Ericsson, all named as technology partners, a detail worth pausing on, since it means even non-Chinese equipment makers are participating directly in the specific test bed. The network has reportedly been used to test real-world scenarios including low-altitude drone inspection, industrial manufacturing coordination, and holographic communication, moving the research from pure technology validation into what engineers call system-level capability testing, the stage where individual breakthroughs either combine into something coherent or expose problems nobody anticipated in isolation. The regulatory side of the story moved just as fast, which matters just as much as the engineering, since spectrum without regulatory clearance is simply unusable no matter how impressive the underlying science is. In May 2026, China's Ministry of Industry and Information Technology granted the country's IMT 2030 Promotion Group, the official body coordinating 6G development nationally, access to experimental spectrum in the 6 gigahertz band for outdoor testing, a step that lets prototype base stations and devices be evaluated well beyond sealed laboratory conditions. By July 2026, the ministry confirmed China had moved into the second phase of its national 6G trial program, following a first phase that had already produced what officials describe as a reserve of more than 300 distinct 6G-related technologies, spanning everything from new antenna designs to integrated sensing techniques. Separately, researchers at Peking University and the City University of Hong Kong unveiled what they call the world's first 6G chip prototype, a device measuring just 11 millimeters by less than 2 millimeters, capable of operating across an extraordinarily wide frequency range from 0.5 gigahertz up to 115 gigahertz, and delivering speeds up to 100 gigabits per second on its own. A meaningful step toward hardware that could eventually be small and efficient enough to fit inside a consumer device rather than a research rack filling half a room. None of this means 6G is arriving next year. It means the specific technical building blocks, the spectrum, the hardware, the outdoor networks, and the chips are now being tested together as a system rather than as isolated lab demonstrations. And that shift is exactly what separates this moment from every earlier terahertz announcement that came and went without much follow-through, where the rest of the world actually stands. China is not running this race alone, and understanding where everyone else stands is what keeps this story honest rather than one-sided. In the United States, the NextG Alliance, an industry group formed by companies including AT&T, Apple, Google, and Qualcomm, has been coordinating 6G research and pushing for early access to spectrum, though the American approach has leaned more heavily on private industry coordination than the large, centrally funded national testbeds China has built, reflecting a broader difference in how the two countries typically approach infrastructure build-outs of this scale. South Korea's government has committed public funding toward 6G research with an explicit goal of contributing meaningfully to whatever becomes the global standard, building on the country's earlier reputation as one of the fastest movers. During the 5G rollout, Finland, through the University of Oulu's long-running 6G flagship program, one of the earliest dedicated 6G research efforts in the world, launched back in 2018, continues to produce foundational academic work that much of the rest of the global research community, including Chinese institutions, actively cites and builds on, a reminder that this field still runs on genuinely international scientific exchange, even amid the broader competitive framing. The European Union has run its own coordinated effort under a research program called HexaX, bringing together telecom equipment makers, universities, and mobile operators across the continent, and Japan has pursued its own national roadmap in parallel, with domestic carriers targeting early 6G trials tied to major public events. What genuinely sets China's push apart is not necessarily raw scientific originality, since terahertz communication research has been pursued by multiple countries for years, and much of the underlying physics is shared, openly published knowledge rather than a secret. What sets it apart is the scale and coordination of the build-out. China has paired its laboratory breakthroughs with binding national planning. 6G is explicitly named as a priority technology in the country's 15th five-year plan covering 2026 through 2030, alongside quantum computing and next-generation AI, and back that plan with dedicated spectrum allocations, city-scale, test networks, and targeted regional investment funds, all moving on a coordinated public timeline rather than depending on individual companies to self-fund research at this scale. According to statements from Chinese officials earlier this year, the country holds close to 40% of all global patent applications related to 6G technology, a figure that, if it holds up as formal standardization proceeds, would give Chinese companies significant influence over whatever technical specifications eventually become the actual global 6G standard. The same kind of standards setting influence that shaped who profited most from 4G and 5G rollouts worldwide, since companies holding patents essential to an agreed international standard typically collect licensing fees from every other company building compliant equipment. The honest limitations nobody should skip past. A laboratory record of over a terabit per second is real, but it comes with caveats that matter enormously once you try to imagine this technology working outside a controlled test environment. Terahertz waves have exactly the same fundamental weakness that already limited 5G's highest frequency millimeter wave band, only more severe. They travel extremely short distances before losing usable signal strength. They struggle to penetrate walls, and they can be significantly degraded by rain, fog, or even humidity in the air, since water molecules absorb energy particularly strongly at many terahertz frequencies. A network built on these frequencies would likely require an enormous density of small transmitters, potentially one every few dozen meters in dense urban areas, a build-out cost that dwarfs even the expensive millimeter wave rollouts telecom companies already scaled back once during the 5G era, and one that becomes considerably harder to justify economically outside of dense city centers. There's also no finalized global 6G standard yet, and there will not be one for several more years. The International Telecommunication Union's framework for 6G, known as IMT 2030, lays out the target performance goals and use cases the technology needs to hit, but the detailed technical standards that equipment makers worldwide will actually build hardware against are still being negotiated inside international standards. Bodies like 3GPP, with formal completion generally expected around the end of this decade. Every number coming out of Nanjing right now, however impressive, describes a research prototype operating under controlled conditions, not a finished, interoperable, global standard that a phone manufacturer in another country could simply build a chip against tomorrow. History offers a useful caution here too. Early 5G demonstrations in the mid-2010s also produced eye-catching peak speed numbers in lab settings years before ordinary consumers saw anything close to those figures on a real device, and the gap between a laboratory record and a mainstream product has consistently proven wider than early headlines suggested. Cost and power consumption present their own separate hurdles. Generating and processing signals at these frequencies takes considerably more power per bit of data than existing 5G equipment, an issue that becomes serious once you're talking about deploying millions of small transmitters rather than a handful of lab benches drawing power from a dedicated research grid. And consumer chips capable of handling terahertz frequencies at low cost and low power, the kind that would need to fit inside an ordinary smartphone rather than a research rack, are still years away from mass production, even accounting for the promising early prototype out of Peking University, which remains a proof of concept rather than something ready for a factory production line. Why this still matters, even years before launch. It would be easy to file this story away as another impressive but distant Chinese lab announcement that misses what has actually changed over the past few years. Terahertz communication sat in that awkward, ignored gap in the spectrum for decades, treated as an interesting curiosity rather than a practical engineering target. What has shifted since 2022 is that a sustained, well-funded research program has methodically moved that curiosity from a single lab bench to a repeatable world record to an outdoor city, scale test network to a national spectrum allocation, and a formal place in a 5-year economic plan. Each step closed a specific gap that used to make terahertz communication sound like science fiction. The countries and companies that end up shaping the final 6G standard, the actual rules. Every phone, base station, and chipset in the world will eventually be built around, stand to gain enormous influence over the next decade of the global telecom supply chain. The same way whoever led 4G and 5G standardization captured an outsized share of the licensing revenue and equipment sales that followed. That is the real stake behind a number like 1 terabit per second. It is not really about how fast your phone might download a movie sometime around 2030. It is about which countries' research institutions, patent portfolios, and equipment makers end up writing the rulebook that the rest of the global wireless industry has to build against for the next decade after that. If this changed how you think about the next generation of wireless technology, hit the like button and subscribe so you do not miss the next deep dive. There are more videos on the screen if you want to keep exploring. Here is a question worth sitting with. Do you think China's head start in outdoor 6G testing translates into real influence over the global standard? Or does standardization end up spreading that advantage more evenly once every country's research catches up? Let me know in the comments.